1713 is a landmark year in probability. The reason is this foundational book. It brought probability out of gambling and into real life like insurance, law, risk and decision-making. This book introduced one of the first great theorems of probability, the law of large numbers. The book was written by Jacob Bernoulli back in the 1680s, but published only 8 years after his death, by his nephew Nicolaus Bernoulli.
That same Nicolaus, in that same year 1713, was writing to a French scholar, Pierre de Monmort. Among a handful of probability puzzles, he mentioned one little game. That game turned out to be one of the most stunning paradoxes in the entire history of probability and the first real challenge for a brand new branch of mathematics. Today we call it the St. Petersburg paradox, or the infinite sum paradox. And it's a very simple game. Imagine flipping a fair coin.
We start with a $2 pot. If a coin lands tails, I give you the pot, $2. If it lands heads, I double the pot and flip the coin again. If the second flip lands tails, I give you the doubled pot, $4. If not, I double the pot again and we continue. Tails on the third throw and I give you $8. If not, I double the pot and we continue again. So the pot doubles with every head, and the moment the coin lands tails, the game is over and you take whatever is in the pot. 10 heads in a row before the first tails and you get more than $2,000. 20 heads and it's over $2 million.
In theory, the prize could be bigger than any number. But that's not the paradox yet. The main question is, how much would you be willing to pay for a single game? Pause for a second. What does your intuition tell you? $1? $2? $200? Most likely you landed somewhere below 20. But the mathematical answer is infinity. To make the game fair, you would have to pay an infinite amount. This game is literally priceless. Where does this impossible answer come from? How have mathematicians tried to resolve this paradox for 300 years? Why does it matter far beyond gambling? And what does it tell us about the nature of humanity? This is Vital Math. Here we enjoy and explore the beauty of mathematics. The St. Petersburg paradox. Let's go! First of all, why is infinity the answer? Well, it comes from one of the most trusted ideas in probability – expected value.
Expected value is the average outcome of a bet if you could play it again and again. To put it simply, it's calculated as the sum of all possible outcomes, each weighted by its probability. Imagine flipping a coin once. Heads, you win $5. Tails, you lose 1. The probability of both heads and tails is 1/2. Expected value is the sum of outcomes for each of possible future scenarios, each multiplied by its probability. In our case, the expected value is 2. So any price under $2 is good for you. Anything above is definitely a trap.
This simple idea sits behind the casinos, poker tables, insurance pricing, financial markets and a huge part of modern decision-making. But let's get back to our original game.
There is a 1 in 2 chance the game ends on the first flip, paying $2. A 1 in 4 chance it pays 4. A 1 in 8 chance of 8, and so on. Now let's calculate the expected value. It is the sum of all possible outcomes multiplied by their probabilities. What we get is simple and infinite sum of ones, which, as you might guess, adds up to infinity.
So the expected price is infinite, which means that in theory you should be willing to pay infinity to play the game. But let's get a feel for how the game actually behaves. Back in 1777, the French naturalist Georges Louis Leclerc Comte de Buffon ran an experiment in the spirit of early Mr. Beast. He hired a child to actually play the game 2,048 times. Every single game ended up within 9 flips. The average payout was about 5. If this video hits 10,000 views, I'll repeat the experiment myself. No child labor this time. But for now, let's hand it over to our best friend, computer, and run the simulation.
Let's start by simulating just one game. What do we see? We have heads and tails as a sequence of outcomes. This means that we get a payout of $4, and it is the maximum payout and the average payout from one game. Let's simulate another game. It's actually the same as the first one, so the average payout is the same. Now let's try a couple more games. So we see that tails come first, and the average payout starts going down. Let's see what happens in the next few games. Let's just continue looking at how these simulations come out and what is the result of those. As you can see, only a few games have visibly high outcomes, but let's just watch and wait until we get to 2048 simulations. Here it is. So average payout is $14, slightly less, and the maximum is 4,096, which is 12 heads in a row. Not bad, but not anything close to infinity. The other way to look at the simulation is this graph. Horizontal axis shows the number of games from 1 to 2048, and the vertical is the payout for the game. Each dot represents a game. Look, this is the distribution of the payouts. And what we can see is that payouts remains mostly small. Only in a few cases they reach more than $100 and only once more than 4,000. What a time we live in that we can create this simulation in just a few seconds.
So what do we see? On the one hand, the expected price in a single game is infinity. On the other hand, even after simulating so many games, the average payout never climbs too high. So why do we get infinity then? Infinity comes from monstrous jackpots with low probabilities. And our intuition is saying rare outcomes can be ignored. But in this game, every rare jackpot contributed exactly as much to the expected value as every ordinary outcome. The events that are too rare are too large to ignore. That is the gist of the paradox. The expected value is mathematically infinite but practically useless. 3 centuries later, Nassim Taleb would call events like these black swans, rare events with enormous impact. But mathematicians and other scientists had been resolving this paradox for 300 years. Or at least they tried.
Bernoulli's family. This is the most prolific dynasty in the history of mathematics. Over 3 generations, the Swiss from Basel produced an astounding 8 mathematicians. They were so fond of reusing the same names that it's easy to get lost. Jacob Bernoulli kicked off the family's math journey. It is his book we started with. His nephew Nicolaus published that book after Jacob's death, and he was the first to actually write down our coin game. But he was unsure about the solution. He described the prize as an infinite sum and even more than infinity if it is permitted to speak thus. So he shared the problem with his cousin. That cousin was Daniel Bernoulli. In 1738, while working in Russia, Daniel published a paper in one of the leading scientific journals of that time, the Journal of the Imperial Academy of Sciences in St. Petersburg. That journal is how the paradox got its name.
Daniel's idea was beautiful and very reasonable at a first glance. Money, he said, is not worth its face value. It's worth what it does for you.
Picture yourself lost in the desert. The first glass of water is worth everything. The second is worth less. The third, even less again. The same is true with wealth. For someone with $1 trillion, another $1,000 is basically invisible. For someone with $100, that same 1,000 can change the entire life. The more money you already have, the less each extra dollar matters.
So, how do you turn that into math? Daniel suggested that we people are logarithms.
Or at least our perception of money behaves like a logarithmic function. It keeps growing, but slower and slower. So instead of calculating the expected value of raw money, Daniel calculated the expected value of usefulness. And suddenly, infinity disappeared. As Daniel put it, any fairly reasonable man would sell his chance with great pleasure for 20 ducats. Interestingly, Daniel was not the first to have this idea. 10 years earlier, a Geneva mathematician named Gabriel Kramer had described a similar approach in a letter to Nicolaus. Kramer wrote that people of good sense value money by the use they can make out of it. He used a square root instead of a logarithm and got an answer of around 3.
Bernoulli and Kramer were the first to develop the concept of utility, a simple idea that we value things not by their actual price, but by their personal usefulness. 2 centuries later, this idea evolved into expected utility theory through the work of von Neumann and Morgenstern. It became one of the foundations of modern economics, decision theory, game theory, and later the behavioral revolution that won Daniel Kahneman a Nobel Prize in 2002. At first, Bernoulli's approach seemed like a great success. Utility had resolved the paradox. But in reality, this was just the beginning. Over the next 300 years, many other resolutions would appear. Some were very practical. For example, one approach is simply to ignore extremely small probabilities.
Remember Buffon with his 2000 games. After the experiment, he drew a devastating conclusion. A probability small enough should be treated as zero. He even put a number on small enough, anything less than 1 in 10,000. Once you remove these almost impossible outcomes, in our case the priceless game becomes worth about $13. Nicolaus Bernoulli had a similar intuition. Even earlier, he suggests treating anything below about 1 chance in 32 is effectively impossible, and the value of our game in that case drops to roughly 2.5.
Another solution is even simpler. Stop pretending the world is infinite. No casino, no bank, no country has infinite money.
Buffon calculated this back in 1777. If the coin keeps landing heads, by around the 29th toss there would not be enough money in the entire Kingdom of France to pay you. Even very large caps resolve the paradox easily. Cap the total price at $1 million and the fair price becomes about $20. Cap it by the size of the US economy and the fair price is around $44. Cap the total price by the entire world economy and the fair price is still only around $46. Even if you somehow converted all the atoms in the observable universe into cash, the expected value would only be about $266.
This solution makes perfect sense in the real finite world. A related solution is to limit the number of flips. Nobody can flip a coin infinitely many times in reality. In this case, expectation becomes finite as well. Someone else may say the mean is the wrong tool. Use the median outcome instead. The median is only a couple of dollars in our case. This is the price of the game. All those solutions seem reasonable, but then in the 1930s Austrian economist Karl Menger uncovered a big problem with the original solution. He claimed that Bernoulli's solution works only for a particular version of the game, and if you slightly tweak the prices, the paradox reappears again.
Daniel Bernoulli used a logarithm to tame the doubling price. But what if the price grows faster, for example, exponentially? Then the logarithm and the exponential cancel each other out and the infinity returns. Menger showed that this problem is relevant for any utility function that keeps rising forever. Logarithm, square root, anything you like. If your utility curve has no ceiling, then someone can always design a lottery that breaks it. This became known as the Super St. Petersburg paradox. According to Menger, the solution is a utility curve with a ceiling, a point beyond which more money is literally worth nothing to you.
The culmination of resolutions was a publication by economist Paul Samuelson in the 1970s, who claimed that paradox is simply impossible in real life and there is nothing to resolve. So it seems like everyone could find a resolution to their taste. But there is one unpleasant pattern that unites all of these solutions. None of them actually resolves the original paradox. Every single one quietly changes the game itself. Kept the price, kept the bank, kept the number of tosses, bend the utility curve, delete rare outcomes, swap the mean for the median, and it gets even more uncomfortable. Almost none of these are really mathematical solutions. They're coming from psychology or economics. Well, maybe the problem is not the game, but the rule of choice itself. That is what one of the recent approaches is trying to fix. The idea there is to describe human choice as a stochastic process without touching the rules of the game itself. The model calculates the expected length of the game is around 1 or 2 tosses, which is exactly what most people would expect, thus resolving the paradox. Alright, so now we have even more solutions. We can finally sleep peacefully, right? Wrong! It appears that for 300 years we might have been calculating the wrong thing.
In his 2011 paper, physicist Ole Peters argued that the classical expected value takes an average over something that doesn't actually matter to a real person. It averages across many possible worlds rather than following one person through time. Remember Doctor Strange from the Avengers, the one who could look across millions of parallel universes at once. That's exactly what we do with this paradox with expected value. Imagine millions of parallel versions of you playing the game once. Some win $2, some win 4, some win 8, and a tiny number win terrifying jackpots. Then we average across all these parallel worlds, and that is called the ensemble average. And that is where infinity comes from. Among infinitely many possible worlds, there are always a few where the coin lands heads 40 times in a row, and the prize is monstrous. But you, as a real person, do not live across parallel worlds. You live through time. You play once, then again, then again. What matters to you is not the average across worlds. It is how your wealth grows through time. That is the time average. And the main surprise is, for our game, those two averages are different. A system where the time average is not equal to the ensemble average is called non-ergodic. Wealth is non-ergodic. Look at a simple example. Say you have 1 unit of money. You flip a coin, heads you gain 50%, tails you lose 40%, ensemble average is 1.05, plus 5% per round. That's a great game. But now imagine one person playing again and again. Their wealth multiplies. And when quantities multiply, the right average is not the arithmetic mean, it is the geometric mean. So the time average is 0.95, minus 5% per round. You lose 5% on average at each round. Across parallel walls, the game looks profitable. Through time, for one real person, it destroys wealth. Peter shows that the St. Petersburg paradox has the same hidden problem. The infinite expected value comes from averaging across imaginary parallel walls. But for a real person living through time, the relevant value is finite. The most beautiful part is that the time average formula gives the same answer as Bernoulli in his original solution. But now the logarithm is not a psychological utility function. It comes from the mathematics of growth through time. We ended where we started, but with a completely different explanation.
Of course, as with every solution of St. Petersburg paradox, this one has critics too. Some call it old wine in a new bottle. They say long-run growth is just logarithmic utility in disguise, replacing one hidden assumption with another. Today there is still no consensus on what's the single resolution of the paradox that satisfies everyone. But by now you might be asking yourself a fair question. Why bother? Why not just leave this paradox alone? Why do we still try to resolve it after 300 years? Well, because the paradox is not really about a coin game. It's about how we make decisions under extreme uncertainty. And that appears to be relevant everywhere.
In 1994, a former Salomon Brothers bond trader named John Meriwether created one of the most famous hedge funds in history, long-term capital management. Among its principals were Myron Scholes and Robert Merton, the future Nobel Prize winners in economics, the man behind the option pricing formula used across modern finance. For a while, it looked like they had solved the market. LTCM made about 20% in its first year, then more than 40% 2 years in a row, and their models did more than generate profit. They also said a loss big enough to destroy the fund was, for all practical purposes, impossible. Then the impossible happened. In August 1998, Russia defaulted on its debt. Investors panicked. Risky assets sold off together, and that was critical for LTCM. In less than 5 months, a hedge fund lost almost all of its $4.7 billion in capital. To prevent the damage from spreading through the financial system, the Federal Reserve Bank of New York launched a rescue program. The regional investors were almost wiped out, including the Nobel laureates.
Rare events can ruin a hedge fund, and it's not just finance. Expected value is the key behind casinos, insurance, and most of our decision-making. And yet the St. Petersburg paradox exposes a flaw in our most trusted decision rule. It proves that expected value has a blind spot. When a single outcome is rare and enormous, the average stops describing reality. That blind spot is exactly where the real world keeps its biggest consequences. The events that truly shape our lives and economies are rare and huge ones. Catastrophes, venture investments, crashes in the financial markets, and the paradox is the simplest model of that behavior. Handling the tail, what really matters, and where you end up depends on how you do it. I honestly didn't plan to end here, but it's impossible not to. We'll end on the black swans of Nassim Taleb. As he put it, it doesn't matter how frequently something succeeds if failure is too costly to bear. But let's summarize the key takeaways. So what are the 3 things I'd like you to take away from this story of the St. Petersburg paradox? First, the paradox itself. It doesn't come from the math. The calculation is flawless. It comes from the gap between math and our intuition. It's one of the first true paradoxes in probability, and it taught us something uncomfortable. We can't blindly trust even the most basic tool we have, the expected value, the plain old average. Probability is very helpful and powerful, but we should apply it with caution. Second, multiple solutions. Bernoulli and Kramer proposed pricing the game by its utility rather than its face value, and for a while it looked like a good answer. But it turned out to be just one answer among many, and new resolutions are still being proposed today. 3 centuries after Bernoulli, there is still no single solution everyone agrees on. But each solution reveals something important, and together they help shape some of the biggest ideas in modern decision-making: expected utility theory, game theory, behavioral economics, prospect theory, and ergodicity economics. Finally, human nature. At its core, the paradox is an attempt to describe mathematically how we make decisions. And it reveals that even in the simplest possible game that processes anything but simple, are we rational? Are we stochastic? Do we even understand what we are doing? And most importantly, why we behave like that? These are questions still waiting for the best mathematical model, but whatever that model turns out to be, the St. Petersburg paradox will always be the litmus test for new theories. Anyway, be careful when you use expected value, and watch out for the tail. That's all I have for you today. As always, don't forget to like, subscribe, leave a comment and share this video. This would help spread the math beauty even more. Thank you for watching. Think and enjoy the beauty of mathematics. See you next time.